Hi Bob, I've been diving into the quantum computing papers from August 2025 and there's quite a diverse range of research. I'm particularly intrigued by the practical applications emerging. What caught your attention this month?
Alice, it's been a fascinating month indeed. What strikes me most is how we're seeing quantum computing mature across multiple fronts simultaneously. The finance applications in Hellstern and Yeniaris's work show we're moving beyond toy problems, while the hardware characterization studies like Deng's qubit health analytics demonstrate real operational concerns for quantum centers.
That finance paper really stood out to me too. They propose a 4-step framework for assessing quantum solutions in finance. Can you break down why this systematic approach is so important for the field?
Absolutely. The framework addresses computational scalability, error tolerance, data complexity, and practical implementability. Essentially asking, should we use quantum here, rather than, can we use quantum here? This is crucial because quantum advantage isn't automatic. They're also tackling post-quantum cryptography concerns, which is vital since quantum computers will both enable and threaten financial security.
Speaking of practical concerns, I noticed several papers dealing with noise and error correction. The compilation-informed quantum error cancellation work by Camilo et al. Seems particularly innovative. How does their approach differ from traditional quantum error correction?
Camilo's work is brilliant because it's circuit agnostic and uses information about gate compilations to achieve unbiased estimation with constant sample complexity overhead. Unlike traditional QEC that requires massive overhead, their quasi-probability method works with current hardware constraints. The key insight is leveraging compilation knowledge rather than fighting against it.
I'm also curious about the quantum natural language processing work by Chen and Kuo. They compared quantum-inspired models against traditional transformers. Were the results promising for quantum NLP?
The results are nuanced. While transformers still maintain overall superiority with the lowest perplexity, the quantum models showed competitive performance in specific scenarios. QKSAN achieved 0 repetition rates, and QRWKV showed perfect vocabulary diversity in certain tasks. It suggests quantum approaches might excel in specialized NLP applications rather than general-purpose text generation.
The computational chemistry analysis by Gundlach et al. Seems quite sobering about quantum advantage timelines. What's your take on their assessment?
Their framework extension of Choi, Moses, and Thompson's work provides realistic timelines. They find classical methods will likely remain superior for decades, in many cases, but quantum computers will make important contributions in highly accurate computations for small to medium molecules within the next decade. It's a balanced view that acknowledges both quantum potential and classical resilience.
I found Sarkar's work on device-independent certification of quantum gates fascinating. How significant is this for quantum computing verification?
Sarkar's proof of principle demonstration that any quantum unitary can be self-tested device independently is groundbreaking for quantum security. Using quantum networks with multiple independent sources, this provides a fundamental step towards certifying quantum interactions directly from data, without detailed modeling assumptions. It's crucial for building secure and reliable quantum processors.
The portfolio optimization papers caught my eye, both Wang et al. Using VQE and Agliardi et al. With sampling-based approaches. How do these different quantum optimization strategies compare?
Both tackle the NP-hard QUBO formulation but differently. Wang's VQE approach uses weighted CVAR with CMAES optimization, while Agliardi's sampling-based CVAR VQA includes local search post-processing. Agliardi's work is particularly impressive. They achieved 0.49% relative solution error on 109-qubit IBM Heron processors with up to 4,200 gates, showing quantum classical workflows can outperform purely classical approaches.
The visualization work by Schinkel introduces statogram for quantum state visualization. Why is this important as quantum systems scale up?
Schinkel addresses a critical limitation. The block sphere only works for single qubits. His 2D statogram approach visualizes probability amplitudes and phase angles for arbitrary numbers of qubits in a unified framework. As we move toward larger quantum systems, intuitive visualization tools become essential for debugging, analysis, and understanding quantum algorithms like the Deutsch-Josse algorithm he demonstrates.
I noticed several papers on post-quantum cryptography. Ahmed et al. Surveyed PQC support in cryptographic libraries. What's the current state of readiness?
Ahmed's analysis reveals a mixed landscape. While some libraries have integrated NIST-selected PQC algorithms like Crystal's Kyber and Dilithium, others lag behind. The key challenge isn't just implementation, but performance trade-offs and adoption hurdles. This creates potential security risks as quantum threats become more imminent, highlighting the urgent need for coordinated adoption strategies.
The distributed quantum computing compilation work by Zhou et al. Addresses heterogeneous QPU challenges. How significant is this for scaling quantum systems?
Zhou's framework is crucial for the future of distributed quantum computing. By exploiting structural patterns, using clustering for qubit placement, and adjusting mapping with annealing algorithms, they achieved up to 88.40% reduction in objective value compared to baselines. This addresses a fundamental challenge, efficiently mapping quantum programs onto heterogeneous distributed systems.
The entanglement and decoherence study by Marquez Gonzalez examines the delicate balance between maintaining entanglement and mitigating decoherence. What are the key insights for quantum technology development?
Marquez's work highlights how environmental factors like thermal, electromagnetic, and collisional decoherence affect entangled states, including entanglement sudden death. The analysis of quantum noise mechanisms, amplitude damping, phase damping, and depolarizing, provides crucial insights for developing robust quantum technologies where preserving entanglement is essential for reliable performance.
The multiplayer conflict avoidance using quantum walks by Shiratori et al. Is quite novel. How does this extend quantum decision-making capabilities?
Shiratori's work elegantly extends quantum walks to collective decision-making, addressing scenarios where multiple agents choosing the same option leads to inefficiencies. Their novel method using entangled quantum walks completely eliminates decision conflicts in three-player cases, going beyond previous two-player solutions. This demonstrates quantum interference's power in solving coordination problems.
The National Quantum Initiative Workshop Summary by Caput et al. Provides insights into current roadblocks. What are the key challenges they identify?
The workshop identified critical challenges across algorithmic techniques, resource constraints in near-term hardware, and the need for software systems co-design. 7 key topics were highlighted, offering a snapshot of evolving priorities and a shared vision for advancing quantum computational capabilities. It emphasizes the importance of bridging theory and practical implementation.
Gunlick et al. Introduce guided sampling ansatses for VQC. How do these address the challenge of choosing good ansatses for larger systems?
Their guided sampling ansatz depend on system interactions and measured state samples, making them adaptive to the specific problem. The demonstration on hydronium cation with only 200 circuit executions on IonQ area, achieving errors well below chemical accuracy, shows this scale-free protocol's potential for universal quantum control. It's a significant step toward practical quantum chemistry applications.
The quantum relational knowledge distillation work by Liu et al. Seems to bridge quantum and classical machine learning. What's the significance of this hybrid approach?
Liu's QRKD extends classical relational knowledge distillation by mapping features into Hilbert space and computing quantum kernel values. The key insight is that quantum computation is only required during training. Both teacher and student models remain classical and deployable on standard hardware. This makes quantum-enhanced learning practically viable while maintaining deployment compatibility.
The Graybox characterization work by Pathamsut et al. Combines physics-based and neural network models. How does this address quantum device characterization challenges?
Their approach cleverly combines explicit physics models with implicit neural networks to handle unknown noisy dynamics. By training on finite shot measurement data and optimizing gates based on specified loss functions, they avoid model biases of traditional gradient-based methods. The finite shot analysis provides crucial insights for practical quantum device characterization where only limited data is available.
I'm intrigued by the CQ API work by Brown et al. For quantum accelerated HPC. How does this facilitate quantum classical integration?
CQ provides a C-like API that enables incremental integration of quantum computing into classical HPC codes through runtime offloading. It's compatible with strongly typed compiled languages and gives programmers fine-grained control over classical data movement. The reference implementation, CQ SynB, demonstrates practical usage while supporting experimental features like analog quantum computing.
The procedural generation and games paper by Boltrini and Wilton looks ahead to fault-tolerant quantum computing applications. What potential do they see for quantum gaming?
They identify procedural content generation as a promising application area, examining quantum algorithms that could provide computational advantages over classical approaches. Their hypothetical game exploiting quantum algorithms for computing Jones polynomials exponentially faster than classical computers shows how quantum advantage could manifest in entertainment applications within 5 to 10 years.
This symmetry-based taxonomy by Kumar et al. Proposes organizing quantum algorithms by their underlying symmetries. How could this classification system benefit the field?
Their taxonomy grounds algorithm classification in fundamental symmetries of quantum state spaces, oracles, and circuit dynamics. By organizing algorithms according to symmetry groups and invariants, they enable characterization of behavior, verification, and complexity through preserved or exploited symmetries. This reflects the deep physics connection between symmetries and conservation laws, while yielding practical benefits for scalable quantum computation.
The Quantum Query Complexity Introduction by Hamoudi covers 4 major techniques. Why is this foundational knowledge important for quantum algorithm development?
Hamoudi's structured introduction to the hybrid method, polynomial method, recording method, and adversary method provides essential tools for analyzing quantum computational power. Query complexity has been key in characterizing quantum speedups from Grover's and Simon's algorithms to recent developments in quantum cryptography. Understanding these lower bound techniques is crucial for both proving quantum advantages and their limitations.
Looking at the broader themes this month, what trends do you see emerging in quantum computing research?
Several key themes emerge. Practical applications are maturing beyond proof of concept, with finance and chemistry leading the way. Hardware characterization and noise mitigation are becoming increasingly sophisticated. There's growing focus on hybrid quantum classical approaches that leverage the best of both paradigms. Post-quantum cryptography is gaining urgency, and we're seeing more realistic assessments of quantum advantage timelines.
The integration of machine learning with quantum computing seems particularly active. Are we seeing genuine synergies or just applying quantum to classical problems?
It's a mix. Some work like quantum relational knowledge distillation and quantum flow matching shows genuine synergies where quantum properties enhance classical ML. Others apply quantum methods to classical problems with mixed results. The NLP work shows competitive but not superior performance. The key is identifying where quantum properties like superposition and entanglement provide genuine advantages rather than just novelty.
What about the hardware and systems level research? There seems to be significant focus on practical implementation challenges.
Absolutely. The qubit health analytics, flux crosstalk characterization, and distributed quantum computing compilation all address real operational challenges. We're moving from can we build quantum computers to how do we operate them reliably at scale. This systems-level focus is crucial for transitioning from research demonstrations to practical quantum computing infrastructure.
The error correction and fault tolerance research seems to be evolving beyond traditional approaches. What innovations stood out to you?
The composable fault tolerance framework by He et al. Is particularly significant. It decouples probabilistic noise analysis from combinatorial circuit correctness, enabling easier composition of independently analyzed gadgets. The logical accreditation work provides scalable certification for fault-tolerant computations. These represent more sophisticated practical approaches to quantum error correction.
Looking ahead, what do you think are the most promising directions based on this month's research?
I see 3 key directions. Hybrid quantum classical algorithms that leverage each paradigm's strengths, practical applications in finance and chemistry where quantum advantage is becoming clearer, and sophisticated error mitigation techniques that work with near-term hardware constraints. The focus is shifting from proving quantum computing works to making it work reliably for real problems.
Thanks for this comprehensive overview, Bob. August 2025 really does seem to mark a transition toward more practical, systems-oriented quantum computing research. The diversity of applications and the focus on real-world constraints suggests the field is maturing rapidly.